Yes, what's going on?
Much.
Welcome to class, man. How's your weekend?
They're just full of schoolwork, so wasn't much fun, but
It was fall break.
yeah, but I had too many classes.
Well, sorry to hear that.
I
What? At least it made it less stressful. The fact that you had like one day off or whatever.
yeah, I was able to catch up.
I'm
I'm not
sorry that
sh-
I totally forgot fall break was a thing. I 100% because we don't go to we're not like an in-person thing. I absolutely forgot fall break was a thing, which is why I made your homework due Tuesday instead of Friday. So I hope that helped. Although honestly, it probably would have been nicer to get it done earlier anyway. So maybe I should have kept it. What do you guys think?
well, I haven't got it done yet.
So I guess it worked out.
Yeah.
Wait, what
Anyway,
happens?
was that Herman?
What happens? There's something about something's not due when?
Oh no, I think I seen you guys' announcement. The written assignment 7, which I originally had to do Friday. I forgot Friday was fall break, so I extended it till Tuesday. So tomorrow.
Okay, I see.
Yeah, yeah. But the question always is like, is having an extra 3 days to do it a blessing because you have 3 extra days to do it, or is it a curse because now you're gonna think about it for 3 days?
I finished it on Friday and
There you
submitted
go.
it, so
See,
pretty easy.
deadlines are a total blessing sometimes. When Kennedy was like, we're going to go to the moon in this decade, originally, the engineers were like, who told him to say that? Oh, God. It's going to be like, but they did it, and it was cool. Otherwise, we'd probably still be trying to do it. But we got it out of the way, and now I guess we never need to do it again, sadly. Elon Musk is going to go, right?
Yeah, probably.
well, did anyone have a good fall break? Safa, Benet, Herman?
Yeah, mine was good. Originally, I was gonna do all that homework Friday. I haven't done it yet, but I will do it. But instead I got to play football, so that's kind of a blessing. I hadn't played in months, so it was like it was nice.
Flag football, touch football. What are we talking about?
Yeah, two-hand touch.
Nice, man, dude. I, I very much miss the days. I mean, like there's like I guess I could join it like an intramural sport, but I miss the days of like recess. Where it's like go out and you just get to play flag, like get to play two-hand touch football every day.
I miss that too.
That was the bomb. Now it's like a thing. Now it's like if you want to call up your once they get to college or maybe even high school, it's like if you want to call up your buddies and be like, hey, I want to play two and touch football, it's like it becomes an event. It's not just like a thing you do. It's like, oh, okay, well, I guess we have to think of a time and where to meet and stuff like that. We all have busy schedules. I don't know. This is why adults should still have recess. Like, I still haven't gotten over this. Like, in middle school, I should have gotten over this. I'm still not over the lack of recess. But anyway, we can get our energy out in different ways, like math. So does anyone have more questions? Then we'll just get started because today, I've been saying this for like 3 days now. Today, we are for sure going to get to the basically hands down most beautiful proof of math. I think it's the most beautiful proof of math, the most beautiful I've seen. And I haven't really seen anyone argue against it. I think maybe some people are like, it's actually top 2. The point is, it's pretty great. And the other one we're also going to get to today. So let's get started with it. Before we get to that, though, we're saving that to the end as the kicker. Let's finish up talking about this whole even odd mess we've been talking about. So first of all, we are in section 4.7 still, which is indirect proofs. And that basically means contrapositive and contradiction. All the contras, which sound like a G.I. Joe villain to me, Contra. But anyway, yeah, so that's what we're doing. And then last time, we kind of talked about how we've been using this fact. I'll write it down. We've been trying to prove that the opposite of being even is being odd, right? Like we kind of use that fact, but nowhere have we proven it. It's not immediately obvious, right? The definition of odd or n even, that means n equals 2k for some integer k. N odd, that means n equals 2k plus 1 for some integer k. Or maybe I'll use t. The point is 2 times some integer plus 1. That's what even means, that's what odd means. But from this definition, it's not inherently, immediately, totally obvious that being even and odd are opposites. Right? To be an opposite, what I mean is it's the negation. So i.e., what we're trying to say here is, what we're trying to say is that for all n and z, the opposite of n being even is equivalent to n being odd. Right, that's what we're trying to prove. It makes a lot of sense to us, right? Like even and odd are almost like go-to examples, not just in math, but in life for things that are opposites. But why? Well, like why do they have to be opposites? Well, first of all, note this breaks down in saying that for all n and z, not n even implies n is odd. And for all n and z, n odd implies not n even. Does that make sense? We're just breaking the biconditional into if thens. Now, so we really need to prove that if n is not even, it's going to be odd. And if n is odd, it's not going to be even. Now, one of these we actually proved last time. Can anyone enlighten me in the class?
It was number 2.
Yeah, exactly. Recall last time we proved that for all n and z, we don't have n even and n odd. You might ask, wait, well, how does that relate to this? Well, remember that n odd implies not n even. Well, how can we break that down? Well, remember, this is equivalent to, like P implies Q is equivalent to not P or Q, right? This is equivalent to not in odd, not in odd, or not in even, which by De Morgan's law is the same thing as not in odd and in even. The point being, if you show that every integer can't both be odd and even, then if an integer is odd, it's got to not be even. Because if it was, then they'd have an integer that's both even and odd. We know we can't have that. Does that make sense how we've proven this second part? Hope it does. So now all you have to do is prove the first part. That if n is not even, then it must be odd. And by the way, that's the same thing as saying that if we have not an even implies and is odd, that's the same thing as proving that not an even or an odd. Not an even is the same thing as an even or an odd. So proving that n not even implies n is odd is the same thing as proving that every integer is either even or odd. Does that make sense? And these two facts together are all we need, right? Like the idea of saying the opposite of n being even is n being odd, right? Like this original black conditional here, that's the same thing as saying that every integer is either even or odd, but not both. Because then you know if n's even, well, then it's gotta be, or you know that if n's not even, it's gotta be even or odd, but it can't be even, so it's gotta be odd. Hope that makes sense. So the point is, we're gonna prove this. Oops. We're gonna prove this right here, that if n's not even, n's odd, and that's the same thing as proving that n is that every integer must be even or odd. And once we've done that, we've proven this, and we've actually proven that being the opposite of being even is being odd. The thing we've been using a ton. It makes total sense, but it's actually not obvious. Any questions on the goal? Good. Now, technically, I've heard that when setting goals, it's good to write your goals down, which you just did, which is good. But it's not good to write it's not good to make your goal something that's like necessarily like an actual like number to hit or something like that, because you might fall short. It's instead, you can't really control that. What you can't control is what you can do. For example, it's not good to make your goal like, hey, I'm gonna do I'm gonna be able to do 1,000 push-ups in an hour or something like that by the end of October. That's not a good goal. A better goal is that I'm going to improve my push-ups every day or something like that, because that's something you can do. Or you need rest days, but you know what I'm saying. So anyway, but I believe in us, so let's not care about any of that. So the point is, the claim we're trying to prove is that every integer is even or odd. Gotta be one of them. The formal statement being, for all n and z, and even or n odd. Not that hard. Not that hard to state, at least I should say. Let's start talking about how you'd actually prove this. Aside. So what this really comes down to is kind of like what we were talking about before, right? All we really have to show to prove this is that if n is not even, then n's odd. Because note, if n even, then n even or n odd, so it works, right? So we really have to show that if n not even, n must be odd. And we could do this the other way around, by the way. We could note that, hey, note like if n's odd, then n's got to be even or odd, so that works out. But if n's not odd, it needs to be even. Either way, we either need to show that if n's not even, it's odd, or if n's not odd, it's even. Yeah. So let's go about this. Now, first of all, you might be asking yourself, okay, wait a minute. So I'm trying to show here that if n's not even, it must be odd. So I'm trying to show that for all n and z, like this second statement here, is that for all n and z, not n even implies n is odd. You might notice, hey, we're in the contrapositive contradiction section. So, hey, we have an if then, let's try contradiction. Maybe that'll make it easier. But if we do that, we'll actually just get n not odd implies n even, which is basically just as hard. So contradiction is not going to give us much here. Or sorry, contrapositive is not going to give us much. Contradiction, here's exactly why I want to do this example. You can kind of use indirect proofs as tiny pieces of a larger whole. So your whole proof doesn't have to be proof by contradiction, but one piece of your proof could be a tiny little proof by contradiction. You're going to see that in a second. But for now, let's get going with this. How to show that if n's not even, n must be odd. So let's assume n not even. What's this mean? Well, n even means there exists a k such that n equals 2k. And not even must mean for all k in the integers, n does not equal 2k. Or another way to put it is 2 does not divide n. All right. But let's look at this. Let's get some colors up in here. Let's look at a number line. And notice that evens are in red here, right? Evens are the reds. If you take any odd number, like 3, how far away is it from an even number?
It's 1 away.
It's got to be 1 away, right? Every even number is within 2 of another even number. So if you're not even, the most you can be is within 1 of an even number, right? They're actually within 1 on both sides. But kind of the one we care about more is the one below it. So notice that 3 equals 2 plus 1. It's an even number plus 1. And we care about that because that means it's 2 times 1 plus 1, so it's odd by definition. 5 is 4 plus 1. 1 plus an even number, that's going to be 2 times 2 plus 1. So kind of the thing to notice is that every odd number, that everything that's not even has to be 1 bigger than an even number, just because of the way the evens are so close to each other. The evens are all spaced by 2. The question is, though, how do we show that? Right? And that's where it gets difficult. But let's think about this. Yeah, think about this. because what we really need to do is we need to take an arbitrary, not even number. So n's an arbitrary, not even number. And we need to show that there must exist some k star need to show there must exist some k star in Z such that n equals 2k star plus 1. And here is the clever bit. Here's how I'm going to do it. We can think about it forever, but here's a really interesting thing to look at. And that is, let's look at the set of all k's in the integers such that 2k is less than or equal to n. Why do we care about this? Well, if we draw the number line again, we look at that and we make like a 3 be our n, then our s in this case, well, let's think about it, right? Like we could do, so we're looking for all the k's in Z where 2k is less than or equal to n. So like, let's look at the 2k's, right? The 2k is just the even numbers. So this is a 2k that's less than or equal to n. This is a 2k less than or equal to n. This is a 2k less than or equal to n. This is a 2k less than or equal to n, right? And all of these have k's associated with it. Here, if 2 equals 2k, k equals 1, k equals 0, k equals -1, k equals -2. The point being that here we're just looking at all the possible k's where 2 times k is less than or equal to n. The reason we care about that is because the biggest number in this set will be the number that if you multiply it by 2, it's as close to n as you can get. As we just talked about, that difference should be 1. So notice here, right, the biggest k that works is k equals 1, because that gets you to 2. If you try to use k equals 2, you get 2 times k, which is 2 times 2 is 4, bigger than our n, which is 3. So the biggest k that you can multiply by 2, and it'd be less than or equal to n, is k equals 1. But then notice that 2 times 1 is 2, plus 1 equals 3. The point is, the max k in here times 2 plus 1 should be in. How are you feeling? Isn't making any sense? All I'm saying is, let's try to find the biggest even number less than n. That's all this is. Let's try to find the biggest even number less than n. Or really the k that leads to it. The biggest even number less than n. And what we want to show is that if you add 1 to the biggest even number less than n, you get n. Another way to put this is want to show the biggest 2k less than n otherwise known as biggest, even, less than n, plus 1 is n. How are you feeling about that? Does that idea make sense? That if we show the biggest even less than n plus 1 is in fact n, well then we've just found we just show that n's odd, because being odd and even being even plus 1 basically. Okay, well, this is making sense. So the point then is that, let's look at this. Let's define K star to be the max of S. So that just means the biggest number in S. And now our goal is to show that K star, so now I want to show two K star plus 1 equals n. Now here's how I'm going to do that. I'm going to do that by contradiction. So another way to look at this is this implies, this is the same exact thing as saying that n minus 2K star equals 1. Let's prove this by contradiction. So this is what I'm talking about. This little claim right here, this little claim is what we're going to use a contradiction proof on. So let's assume the opposite. Assume that n minus 2K star is not equal to 1. Thus, if n minus 2K star is not equal to 1, what does it have to be? Like, for example, if A does not equal 1, what does A have to be? What can we say about it in relation to 1? I'll give you a hint. There's two things it could be.
It has to be odd then, right?
Well, just using this fact that A is not equal, like forget about all this. Let's just look at this. Just using the fact that A is not equal to 1, like the opposite of being equal to 1.
Not equal to 1?
What do you say?
Or it is equal to 1? I guess like the opposite is it is equal to 1 or it is not equal to 1. That's the only two things.
Oh, sorry. Yes, so the opposite of being equal to 1 is that it's not equal to 1, obviously. But what that means is, think about this, right? Like, you know how toddlers go, like, how old are you? I'm this many. Like, if you're not this many, if you're not 4 years old, what are your options for ages?
Everything else?
Everything else. You're either older than 4 or younger than 4, right? If A doesn't equal 1 and A is an integer, this is the same thing as A being less than 1, or since it's an integer, we can say less than or equal to 0, or A is greater than or equal to 2. Does that make sense? Like, and same deal with if A doesn't equal 4, if you're not 4 years old, well, then you have to either be 3 or less, or you have to be 5 or more. That makes sense, right? I think that makes sense. The point being Since n minus 2k star is not equal to 1, and n's and n minus 2k star is an integer, the reason integers matter is, of course, well, because like if a doesn't equal 1, but a is just a real number, it's not necessarily an integer, well, then you have to use greater than 1 or a is less than 1. We can't say that it's greater than or equal to 2 because, for example, 1.5 would work. That would be a number that's not equal to 1. Yeah. So, thus we have that n minus 2k star is greater than or equal to 2, or n minus 2k star is less than or equal to 0. Let's disprove both of these independently or individually. If we prove this can't happen and this can't happen, and they both lead to contradictions, well, then this whole statement can't happen. And if this can't happen, that means n minus 2k star must in fact equal 1. We were that assumption, n minus 2k star does not equal 1, is false. It could not happen. So here's the idea. Let's look at this first. If this is true, that would mean that n is greater than or equal to 2 plus 2k star, right? Which means that n is greater than or equal to 2 times 1 plus k star. The whole proof, the key idea of the whole proof happens right here. What's the problem with this? Remember, we're trying to reach a contradiction. Assume this is for contradiction's sake that this happens. When this happens, this or this happens. I'm trying to show both of these avenues lead to contradictions. So why does this one's easy, this is going to be easier, this one's the hard one. So if we have this, we know we have this. Why is this a contradiction?
Is it our set?
Is what?
Is it our set?
It definitely has to do with the set, Benet. Exactly. What about the set? Oh, you got it.
We say that 2k is less than or equal to n, but then here we're saying that n is greater than or equal to 2 times 1 plus k. Am I crazy? Is that not a contradiction?
Yeah, so n is greater than or equal to 2 times 1 plus k. What's that mean about 1 plus k? Or 1 plus k star?
It's even?
We don't know it's even. Can someone help him out? If n is greater than or equal to 2 times 1 plus k star, 2 times this number, based on s, what do we know about 1 plus k star?
Not even? I'm confused.
No idea if k, like here, k star is the maximum of this. We have no idea if k star is even odd. We don't really care. What is s? S is instead of all integers, instead of all numbers in the integers, that you can multiply by 2, and it'll be less than or equal to n. Well, 1 plus k star is an integer that you can multiply by 2, and it's less than or equal to n.
Is it that we have like 2k is less than or equal to n, but we also have 2 times 1 plus k is less than or equal to n?
You're so close. You're so close. Here's the thing. We know that 2 times 1 plus k star is less than or equal to n. So 1 plus k star is an s. Right? Because s is just instead of all numbers, you can multiply by 2, it's less than or equal to n. 1 plus k star, based on this assumption, is a number that is it's a number that you can multiply by 2, and it'll be less than or equal to n. So by definition of s, 1 plus k star is ns, right?
Does it get weirdly recursive? Is that the issue?
No, it's fine.
Okay.
But does that make sense? The whole like we like does this make sense that 1 plus k star is ns? Who doesn't see it? Makes sense, Benay? Herman, Justice, Afra, Safa?
I'm confused.
Same.
Same? I'm so glad you mentioned something. Good. This is, I mean, this is a confusing proof. But so S is the set of all integers that you can multiply by 2 and be less than or equal to n. So for example, let's make it real for a second. Like if n equals 5, right? Then S, which is the k and z, such that 2k is less than or equal to n, which is 5. And what's that going to be? Well, that's going to be, well, if k is negative, then it'll be 5. So it'll be like -2, -1, 0. Notice that -2 times 2 is -4, which is less than or equal to 5. -1, I really want dots here. -1 times 2 is -2, less than or equal to 5. 0 times 2 is 0, less than or equal to 5. 1 times 2 is 2, which is less than or equal to 5. 2 times 2 is 4, which is less than or equal to 5. 3 times 2 is 6. Oh, 6 is not less than or equal to 5. So this is what S says in this case. In the case where n equals 5, S is everything up to 2. All the integers up to 2, because after that, you can no longer multiply 2 by these integers and get something less than or equal to 5. So this is what S is. All numbers you multiply by 2, that gets you less than or equal to 5. Now, K star in this case, K star we define to be the max of S. So in the case where n equals 5, K star is going to be what?
2.
2, exactly, right? The max of the set, 2. But then, let's assume, we're under this assumption. Assume n minus 2k star, in this case, yeah. Assume that n minus 2k star, which is 2, is greater than or equal to 2. Well, that would mean that n is greater than or equal to 2 plus 2 times 2, which equals 2 times 2 plus 1, which equals 2 times 3. The point is, this would mean n, by the way, equals 3 here, or 5. So when n's an actual number, we can see, oh, obviously, 5 is not greater than or equal to 6, right? And since 5 is not greater than or equal to 6, this assumption must be wrong. This assumption right here. N minus 2k star is greater than or equal to 2. In our case, that's saying n minus 2k star greater than or equal to 2. That's saying that 5 minus 2 times 2 is going to equal to 2, which should be saying that 5 is greater than or equal to 2 times 3 based on the math we just did, adding the 2 times 2 to that side. And this is obviously not true. 5 is not greater than or equal to 6. So our n minus 2k star can't be greater than or equal to 2. But with integers, with actual integers, it doesn't really matter much. But that actual integers, because obviously this is true, I'll move on. But over here, these aren't just like actual numbers we can look at. Here we can say, oh, 5 is definitely not bigger than or equal to 6. So this is wrong. Therefore, this assumption's wrong. Here it's not so obvious. Like, why is it that n can't be greater than or equal to 2 times 1 plus k star? Not so obvious that that's false. But look at this. In this case, if 5 was greater than or equal to 2 times 3 star, this means that 3 is NS by definition, right? The definition of being an S is you're an integer that you can multiply by 2 and be less than or equal to 5. Well, 3 is an integer, you can multiply by 2 and be less than or equal to 5. So this means 3 is an S. But we know that 3 is not an S because 2 was the biggest number in S. This is a contradiction. If we assume this is true, then we get that 5 is greater than or equal to 2 times 3, which implies 3 is an S. But we know 3 can't be an S, therefore our assumption must be wrong because it logically led to something that was false. Does this help?
So, quick question.
Yeah.
For our actual proof on the left side, are we now able to prove that 1 plus k should not be an S?
Exactly. So for our proof on the left side, right, the analogous thing to do, right, this shows right here that by definition, 1 plus k star is an S because it's a number you can multiply by 2, make something less than or equal to n. But why does this contradict? Like, what's the contradiction here? What's k star? It's not rhetorical. Like, what's k star defined to be?
It should be the max value, so we shouldn't be able to add another one to it, right?
Exactly. K star, yes, exactly, Benet, yes. K star is the maximum element of S. That's how it's defined. It's just, we know there's going to be one, defined to be that. In this case, it was 2. 1 plus k star is going to be bigger than k star. So if it was in S, that would mean that k star is not the max, but 1 plus k star is. The point is, this can't happen. It's contradiction since k star is the max in S. So,
I have a quick question.
yeah, please, Herman.
So 1 plus k star, so if that's the max, let's say it's 2, which then becomes 3, which means 3 is the max. And can we plug it back in and say that 3 plus 1 would be 4, and then we could just keep going forever? So there's also kind of another weird...
That's the crux of the exact problem, right? That's another way you can look at it, right? Is that kind of... Yeah, I mean that well, it kind of stops because we assume k star is the max. And since k star is the max, if this assumption were true, 1 plus k star would also be an S. Under this assumption, 1 plus k star is also an S. But we know that can't happen because k star is the max. And 1 plus k star would be bigger, so it just can't be an S. So the contradiction there. But you're right that if you think about like, oh, okay, well, if this is wrong, then 1 plus k star, like if this assumption was true, like it's kind of like we define this to be true. So this is like a fact. This is a fixed point. This is the assumption we're trying out. So kind of, Benet. So this is kind of an assumption we're trying out. Like, let's just try out, see if this is true, what happens, right? Well, if this is true, you get a contradiction. You get that k star wasn't actually the max. But if we kind of look at it the other way, if we consider this to be a fact, well, then the problem is that you're right, that if this is a fact, if you're to say, oh, well, actually k star wasn't actually the max, k star plus 1 is, well, you plug that back in, and then k star plus 1 is actually the max. K star plus 1, it will be an infinite problem, And that's another reason that's kind of the exact problem, is the fact that K star is the max. You can't keep adding 1 to it. It kind of depends how you look at it, but you're totally right that that's an issue. If you look at it a different way, it's kind of confusing. I think it's easier to look at it as K star is the max. K star is the max. That's a fact. So 1 plus K star can't be an S.
Yeah, both make sense. It's just kind of cool. Just know.
Good. Yeah, no, it is kind of cool. Yeah. So this is why this is our contradiction. This can't be true. The difference between n and K star must be greater than or equal, cannot be greater than or equal to 2. So this is false. This can't happen. But maybe this happens. Let's look at the problem with this. If we assume this, well, that means that n is less than or equal to 2K star. But remember, K star is in S. So what do we know about 2K star? Every element of S, if you multiply by 2, what do you know? Based on this definition of S. Remember, S is all the integers such that if you multiply by 2, it's less than or equal to n. K star is in S. It's an integer in S. So if you multiply it by 2, what should happen?
It should be less than or equal to n.
Should be less than or equal to n. So we should get this too. And this is since K star is in n. What's the problem here? The problem here is that 2K star is less than or equal to n. So if n is bigger than or equal to 2K star, and n is less than or equal to 2K star, the only option is that n equals 2K star. But then that means that 2 divides n. But at the very top, we assume that 2 does not divide n. This can't be true. Contradicts assumption that n contradicts that n is not even. Meaning this assumption right here is also not true. So we've shown that n minus 2K star cannot possibly be bigger than or equal to 2. And we showed that n minus 2K star, the difference between n and 2K star can't possibly be bigger than or equal to 2. And it cannot possibly be less than or equal to 0. Both lead to contradictions. Meaning n minus 2K star cannot not equal 1, meaning n minus 2K star must equal 1. N minus 2K star must equal 1. And what's that mean? That means n equals 2K star plus 1, meaning n is I. So the point is, if you assume that n is not even, well, then let's just look at the even number closest to n, the biggest even number less than n. The difference between n and that even number can't be bigger than or equal to 2. Otherwise, there would be a bigger even number in between. And the difference between n and that even number can't be less than or equal to 0. Otherwise, that would mean that if the difference between n and the biggest even number less than n is 0, that means n is that even number, meaning n is even, which can't be true. Therefore, the only option is for n to be an odd number. I did not mean to spend the whole class on this. And to save time, I'm not going to actually write the proof out. write down the formal proof, but it goes exactly like this. What I'll do is I'll write it out on a piece of paper, and then I'll put it on Canvas. I'll put it in the page for this lecture, like for section 4.7, day 3 page. But it goes just like this. But let's get to the most beautiful proof of math, because I have been, which is a lot easier than this actually, because I've been peddling that for days now. So that is the really complicated way to prove that evens and odds are opposites of each other. The most simple statement in the world actually took all that to prove, but we can do it. That proof's not that important. That proof is like the way harder than anything you ever see on a test or anything like that. I just hope that you guys can see the mechanics of like contradiction being used here and there. Anyway, here's the cool proof. Here's the claim. Very simple claim. The square root of 2 is irrational. That's it. Square root of 2 is irrational. What's that mean? It means the square root of 2 is not rational. Meaning it can't be written as a fraction. So, formally what this means is that for all a over b and the rational numbers, the square root of 2 does not equal a over b. And I want to talk about the fact that this is weird. Back in the day, when people were taught, back in the day when people thought about numbers, the very obvious first things to think of are the natural numbers. 0 or like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the counting numbers. And then you can tack on 0 there and you get the whole numbers. And then started the bright idea of, oh, what about the negative numbers too? So, you know, you started out with 0, 1, 2, 3, 4, 5, 6. These are the whole numbers. The naturals plus 0. There's one of the bright idea of, oh, wait, we can also have negative numbers. Like that. But then they thought, what about everything in between, right? Like we know, for example, like if you're an ancient Greek person, you know that if you have, like, if you're looking at cups of water, right, you don't have to have full cups. You could have like a cup and a third of a cup, right? So there's stuff in between the two numbers. But they realized, okay, like I just said, a cup and a third of a cup. Well, we can talk about things in between numbers with fractions of numbers. Instead of one whole cup, it's 1/3 of a cup. Or you could have like 2/3 of a cup, stuff like that. And so people thought, okay, anything in between integers can be written as a fraction. They're a rational number. It's just some fraction of 1. Irrational numbers weren't a thing. People didn't think they existed. Until one guy proved this. How did he possibly prove it? How do you possibly prove that no matter what two integers you divide by each other, it's not going to equal the square root of 2? And the answer is the magic of contradiction. So I'm just going to go through the proof. What are we going to do an aside? Here's the proof. Proof by contradiction. And oh, by the way, I should say we need a lemma here, but the lemma is going to be obvious. And ask me if you want to see a proof for it. Here's the lemma. It basically says every fraction or every rational number, every rational can be written in reduced form. And what's reduced form? Reduced form is like this really means, formally what this means is that for all n and q, n equals p over q, or I'll say there exists P over Q and Z such that N equals P over Q and the GCD of P and Q equals 1, where the GCD is the greatest common divisor. So what we're saying here, all we're saying here is that if you were to do like 30 45ths, I can write that in reduced form.
6/9? No, wait, I lied.
It does equal 6/9. We can keep going, right?
Yeah, 2/3.
2/3. All right. You can always keep reducing fractions until you get to this reduced form. It's called the reduced form, a simplified form. And in the simplified form, the greatest common divisor between the top and the bottom is 1. The reason being that if there was another common divisor, like 6 and 9, we can just divide it out again. So you keep dividing out until you get the greatest common divisor from the top and bottom is 1, and then you can't divide anymore. By definition, the greatest common divisor. Does that make sense? That's some elementary school stuff, right? The fact that you can simplify fractions. That's all it's saying. You can't prove it. Let me know if you want to see that later. But for right now, proof by contradiction. So proof by contradictions, what you do is you assume the opposite. So assume, for sake of contradiction, that there is some N in Q. Maybe I should just make this an N. Or maybe make it a little Q. It doesn't matter. I just want to say rational number. There's some Q in Q such that the square root of 2 equals Q. No, I already don't want that. I want this to be, let's just call it, what's a good letter for, let's call it a X.
Oh.
Yes?
I was saying F for fraction, but that works.
I'll just use X, it's already there. Because F is like a function to me, I don't know. But you see what I'm saying? There's some rational number that, let's say that for all rational numbers, it doesn't equal square root of 2. We're assuming that there is some rational number that does equal the square root of 2. We're assuming the negation. We need to show that negation leads to a contradiction. So, by our lemma, there is some P and Q and Z such that GCD of P and Q equals 1. So the greatest common divisor of P and Q equals 1. Do we all know what the greatest common divisor is? Yeah, it's just the greatest thing that divides both numbers. And so we know the greatest common divisor is 1, and X equals P over Q. Thus, the square root of 2 equals X, which equals P over Q, which implies the square root of 2 equals P over Q by transitivity. Now here's where the fun starts, right? The point is, if the square root of 2 is a rational number, it's gonna equal this reduced form of a rational number. So P and Q have no factors in common. That's the key. But notice this. Consider the square root of 2 equals P over Q. What can we do with this equation to get integers everywhere?
You square both sides.
Square both sides. You do that for any equation. This implies, actually only goes one way now. This implies that the square root of 2 squared equals P over 2 squared by squaring both sides. Which if we evaluate, square root of 2 squared is 2. we can distribute that square to the top and the bottom. So 2 equals p squared over q squared by evaluation. But then we can multiply both sides by q squared, right? We get that 2q squared equals 2 squared by multiplying both sides by q squared. Note, since q is in Z, and Z is closed under multiplication, q squared's in Z. Thus, p squared, which equals 2q squared, is even by definition.
Word's slightly off the.
Thank you very much. All we're saying here is that by multiplying q squared both sides, you said 2q squared equals p squared. Well, this is 2 times an integer. So this is clearly an even number, right? And that equals p squared. So p squared is clearly an even number. Does that make sense? But if p squared is even, what do we know about p?
It's also even.
It's also even. Thank you, Justice. Yes, this is the brilliant part. And this is the thing you guys are going to prove in your homework. We proved a very similar fact that if a number squared is odd, then the original number must be odd. Here we're saying that p squared is even, p must be even. Very similar proof. You're doing your homework, but it's a fact. It makes total sense, I think, right? And that's the key. This little thing that p squared is even, p is even, it kind of works backwards. So we're saying here is, thus, by theorem from homework, since p squared is even, p will be even. Actually, do you mind if I erase so I can get more room here? I'll give it a couple more seconds for writing down stuff if someone's still writing. The big punchline, the first big punchline is that p is even. So if the square root of 2 equals p over q, p's got to be even. All right. So I'm going to put a ... to represent the work we just did. And the punchline was, thus, p is even. And then, by definition, p equals 2k for some k and z. And I shouldn't erase the math. I'm just gonna do the math again. The math we had here, remember, was actually, yeah. This all led to, remember we had considered the square root of 2 equals p over q. And then this all led to 2q squared equals p squared. There we go. So I'll say thus p is even, then p equals 2k for some k and z. This we just got from the simple algebra. Well, then we can keep going with this, right? This means that then 2q squared equals 2k squared by substitution. P equals 2k. So putting 2k in for P here, we get this. But then that implies 2k squared, we distribute that, that becomes 2 squared, which is 4 times k squared by evaluation. And then we can divide 4 by both sides. So we divide 4 by both sides, we get 2 or 4, which is 1/2. I'm sorry, no, we want to divide 2 by both sides. We divide 2 from both sides, right? We get is q squared equals 4 over 2k squared, which just equals 2k squared, by dividing 2 from both sides. Q squared equals 2k squared. What's the meaning about q squared?
Do we say Q is even now?
Q, well, yeah, we're going to get to that, right? But yeah, q squared's even. Because it's 2 times an integer. So note, since k is in Z by definition, and Z close under multiplication, k squares in Z. Thus, q squared, which equals 2k squared, is even by definition. Then, by homework theorem, q is even. Because q squared is even, q is even. So we have p is even, and we have q is even. What's the problem?
If that's both true, then their GCD can't be 1.
Exactly. If both p and q are even, that means they're both multiples of 2. They both share a factor of 2. Meaning the greatest common factor is not 1. Meaning p over q would not be in simplified form. Thus, 2 divides p, and 2 divides q. So GCD of p and q does not equal 1. Contradiction. The point is we assumed that p over q equaled the square root of 2, right? And that p over q shared no p and q shared no factors. The GCD was 1. But we just showed that if p over q did equal square root of 2, then logically what must happen is both p and q must be even, meaning it's not in simplified form. They both share a factor of 2. But that goes against our assumption, right? That goes against our assumption that p and q had a GCD of 1. If you didn't make that assumption, what that'd be saying is that square root of 2 equals some p over q. Maybe the GCD doesn't equal 1. But then you'd get that they both, or the 2 divides both of them, so then you can simplify it, but then you can simplify it again and again and again. We get that infinite recursion thing we were talking about before. But that can stop just by making this assumption at the beginning that p and q have GCD 1. This cannot happen. If square root of 2 equals p over q and GCD of p over q equals 1, then the GCD of p over q is not 1. It contradicts itself, so it can't happen. I was going to get to what we had before. So dot, 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 we kept moving, and we said thus 2 divides p, and 2 divides q. So GCD of p over q, well, really it's got to be greater than or equal to 2, because we know they share a factor of 2. So the greatest common factor is at least 2. Meaning GCD of P over Q is not equal 1. Thus, contradiction. This contradicts definition of P and Q. Definition of P and Q. Thus, assumption is wrong. And what was our assumption? Our assumption was that there exists some x and q, square root 2x equal to x, or square root 2 equal to x. Hence, for all x and q, square root 2 is not equal to x. Done. We are way over time. I am so sorry about that. But how is this proof? Anyone can leave right now. I mean, you can always leave. It's free country. I'm saying I would not be at all upset if you left right now. But the point is, we just proved that no matter which rational number you pick, it's got to be simplified. You can simplify it. But if you do simplify it, that can't possibly equal the square root of 2. You get this contradiction. Saying that the square root of 2 equals x contradicts itself. If you have this, that's saying that you can simplify it and you can also not simplify it. It's a weird thing, right? It's a contradiction, so it can't possibly be true. That's amazing, right? This just feels like we just tricked math. We had this claim that felt impossible to verify. How do you know that it couldn't possibly work for any of them? And we just kind of tricked math a little bit. We just kind of like tricked the universe and go, oh, well, let's think about this, let's think about that. And then it's like catching a witness in a lie. Like we said, we kind of caught math in its own level lies and showed this can't happen. It's amazing. And someone might have died for this. The person that originally proved this, the story goes, they were in this Pythagorean cult, and the cult worshiped numbers. And one thing about it, worshiped integers specifically. And so they thought that every single number, any length you can make, any volume of water, all of that, right? Any single number had to be a fraction. It had to be a ratio of integers because they worshipped integers. Integers had to be the whole thing. But this guy in the cult proved that the square root of 2 was not a ratio of integers. The integers themselves were not enough to cut it, at least not in ratios. They couldn't do every number. And so the story goes they threw him over the boat and killed him to keep him quiet. But which is like, what's that about? But anyway, Pythagorean theorem guy. Yeah, the guy. So the Pythagorean theorem is named after a mathematician named Pythagoras, who actually did not come up with the theorem, but it's named after him. And that actually happens a lot. Like the Archimedean property, I don't think it was actually come with Archimedes. But anyway, it was named to pay homage to him. But anyway, that guy was a famous mathematician. He did a bunch of number stuff, started a number cult, and they might have killed this guy for disproving their whole thing. Which, by the way, is such a anti-math thing to do, because the math is about like a pursuit of knowledge in a certain sense, right? And so if you find out that something you thought was true was wrong, you should be elated by that and then change your beliefs to fit that, rather than try to change the universe to fit when it doesn't. Anyway, that's class. Any questions?
So because there's like this infinite recursion in terms of, so when we try to divide it by 2 and you do the other side and you keep going forever, does that also kind of prove that it never ends, like it goes on forever? Or is that a different?
Good question, Herman. So actually, I'm glad it's after class so I can go into this more. I didn't want to go into it too much before. But basically, if you get rid of the assumption that P and Q is in simplified form, here's what we get. If you get rid of that, or I'm sorry, we didn't even make that assumption. We just know that's true. Let's say we didn't even go that route. Let's say we said prove, assume for sake of contradiction, I'm not gonna write the details. Assume for sake of contradiction, there's an x that equals the square root of 2 with x and q, right? If this x exists, well, just by the definition of rationals, there exists an A and B and Q, and N with, not N, and Z with B not equal 0 such that X equals A over B, since X is in Q. That's just what it means to be a rational number, right? You're a ratio of some integer where B is not 0. Then A over B equals X, which equals the square root of 2. So transitivity, A over B equals the square root of 2. So if we get rid of, see here, we're not stipulating that A and B are specifically in reduced form. We know that does exist integers in reduced form based on this lemma here, and just it kind of makes sense. But but if we don't assume that, right, then we can use our contradiction proof. We can eventually use the contradiction proof to get down to that 2 divides A and 2 divides B in the same way. But instead of having a contradiction, because we never assume that A and B are in reduced form, we never assume that A and B show no factors. We just go, oh, we can simplify A and B a little bit. So then we get that A over 2, like if we let A prime equal A over 2 and B prime equal B over 2, and because 2 divides A, 2 divides B, we can do this, A and B are integers, then we get that A prime over B prime equals square root of 2. But then it would happen again, right? These would also share a factor of 2. So you get like A double prime, B double prime. And that would also share a factor of 2, and you do it again. That would also share a factor of 2, and you do it again, again, and again, and again, and again, and again, and again. And it would never simplify. This would imply that A and B have like infinite powers of 2 in them, right? Which actually does, this is a good point. This is actually a really good point. This kind of shows in a certain non-formal sense that square root of 2 is irrational because the numbers A and B would have to be infinitely big to express it. In the sense that, like, for example, if you took like 0, let's look at digits of pi, right? Like truncated. So 3 equals 3 over 1. 3.1, right, would be like 3. Let's actually, the thing makes it complicated. Let's look at after the 3, like 0.1 equals 1 over 10. 0.14 equals 14 over 100. 3.1415, 0.141 equals 141 over 1,000. 3.1415 is 1,415 over 10,000. You see that the more digits you add to a decimal expansion, the bigger the fractions have to be to express it. Like the bigger the ratio of like the bigger integers need to be in the ratio to express it. You know what I mean? Because it's a more precise number you're expressing. So you need bigger integers to do it. But what we kind of show here is that if A over B equals the square root of 2, well, like A would have to be infinitely big and B would have to be infinitely big to make it work, because you would keep dividing 2 from A. And so because you can divide 2 from A, firstly, you know that A is bigger than 2. But then you can divide 2 from that again, so A must be bigger than 4. You can divide 2 from that again, so A is bigger than 8. And you keep doing that, doing that, meaning A has to be infinite. Same thing with B. They both would have to be infinite for it to work, meaning number one, they're not integers because infinity is not an integer. But also this kind of is a really loose way of showing that these two fractions would have to be infinitely big, because the size, or these two numbers, because the size of these numbers corresponds with how many digits there are. It kind of means that if the fraction has to be infinitely big, well, then the decimal expansion has to be infinitely long. Very loosely. Does that make any sense?
Yeah.
Yeah. So you're totally right. That's related. But kind of the beautiful part is we can ignore this infinite recursion thing and all the consequences of it if we just assume from the get-go that we have it in reduced form, and then we just get a contradiction. Anything else, guys?
Nope. Cool. Thank you.
You're welcome. Have a great day. I hope this was an amazing proof. Oh, cool.
It was good. It was cool.
The first proof was long and convoluted. Looking back on it, maybe we should have just skipped it, but I thought it was interesting. The next proof was short and beautiful. But anyway, have a great day, guys. I'll see you when I see you.
Cheers.